Okay, thank you for letting me present this work about dense 3D ERT to better understand deep landslide structures. So we start with the Viella village, which is a small village located in the Hautes-Pyrénées in France. It is affected by strong slope movement since 2018. This has been triggered by massive rock slide coming from above, modifying the stress strain deformation and also hydrological conditions certainly, and this lead to velocity ranges between 0.5 and 5 millimeter per year. This deformation induce progressive damaging of the building, leading to expropriation in the village. So here are two pictures of the big damage you can see on some houses. Previous investigation on this landslide have been made, and geophysical and hydrogeological study have been performed in 2019. Several 2D ERT and 2D seismic refraction profile have been performed with maximum depth of investigation around 30 meters. Tens of boreholes have been drilled all over the landslide, and all this 2D goes to the conclusion that the Viella village has been entirely built on colluvion. This material is actually made of weathered rocks coming from the progressive collapse of the mountain above. So the bedrock has never been detected either by geophysics or by borehole. Even with the deeper borehole going at 71 meters of depth, the bedrock was not reached. So this study highlights also the fact that the Viella landslide is made of different compartmentalized slides. Some sliding surface have been detected at 25-30 meters of depth, but surface displacement indicates that a deeper sliding surface exists. We also see that an inclinometer is sheared at 54 meters of depth, indicating the existence of this deeper sliding surface. So the objective of the study is to realize a 3D high-resolution image of resistivity of the entire slope up to 150 meters. We would like to image a deep sliding surface of the landslide, also to identify flow paths for a potential remediation. And more generally, we would like to complete the current knowledge on the landslide thanks to large scale and 3D information that we don't have at the moment. About the methodology, we know that the survey area is 800 meters by 800 meters. The resolution required is very high as we are interested in shallow information but also in deep information. As we are in a mountain, the topography is rough and the object of interest is very 3D. So we conclude that the use of standard resistivity meter would require weeks of work and inaccurate result. Inaccurate because you are always making a 2D assumption with the system, and also we will not reach the 150 meter depth of investigation required. Therefore, we choose another approach, which is to measure the electrical resistivity thanks to a full 3D survey using distributed system and using the FullWaver system. So this system is made of autonomous and distributed receivers. Each receiver is able to measure the voltage every 10 milliseconds on 2 channels. Each system is synchronized to by GPS PPS clocks. And so when the systems are set up on the field, they just measure the voltage automatically, and then you just have to use a high power transmitter like this one connected to a high FullWaver that will record the current and to inject between electrode A and B. So the current injected will be displayed here in blue, and the voltage measured by one of these FullWaver on one channel will be displayed here. They are all synchronized thanks to the GPS PPS clock, and then you just have to compute the apparent resistivity from heat. One of the main advantages of the system is that each receiver can be connected to 3 electrodes, so it's measuring on 2 channels that you can put perpendicular. This means that you will record the 2 components of the electric field. If you look at the typical FullWaver survey, you can see that we will inject on the red point inside and outside the survey area, eliminating the medium in all direction, and for each injection measuring the direction of the electric field on each FullWaver. So if we do a simple modeling of this object with an orientation changing with depth, we can compare it to what we call a pseudo 3D survey, where all the different parallel lines are used to construct a 3D model. If we model this and invert the synthetic data, you can see on the inversion that the full 3D setup is more able to image the change of orientation of the 3D object with depth compared to the pseudo 3D setup. So it is one of the main advantages of this system, is to be able to be more sensitive to the 3D object. So then we go back to our field setup. We use 55 V FullWaver, so 165 electrode. The dipole length was 25 meter, and 1 V FullWaver was set up every 100 meter. Channel 1 was north-south direction, and channel 2 east-west direction, to get once again this complete the 2 components of the electric field. And then we once the system are set up, we realize some injection between a moving electrode, so this is all the round red point, and a fixed remote electrode that is triangle, red triangle on this map. So the transmitter station was located in this point. On one side of the transmitter you are connected to the remote electrode, and on the other side you are connecting to the moving electrode, and you are displacing this moving electrode after each injection. So we realize 235 injection every 25-50 meter. So at the transmitter station, you can see a picture here. We had a control computer to check and communicate with V FullWaver by radio. We had a high FullWaver that is actually measuring the current injected by this high power transmitter powered by a motor generator. This is a picture at the remote electrode here. Every morning we had salty water to decrease the contact resistance. Each V FullWaver so is recording 2 channels on at a sampling frequency of 100 Hz. It features a radio communication module for real-time quality control and a schedule start. So the schedule start allows the V FullWaver to start automatically for this survey every day at 8 AM and stop at 8 PM. The 2 teams were running in parallel at the injection, so 2 persons at the transmitter. We needed 2 other persons in each team. We radio communicated by thanks to walkie-talkies. So the signal injected by the transmitter was a 1 second 100% duty cycle, and we injected between 30 and 70 stacks depending on the contact resistance. We measured the GPS position of the electrode with a differential GPS and get a final dataset of 23,970 data points that we acquired in 3.5 days of injection for a total of 5 days on the field to set up and take back the FullWaver. So then after the survey you get the time series of voltage and current. So by Using the FullWaver dedicated software, we computed the apparent resistivity from this time series. We did a careful quality check to check GPS coordinate of electrode. We noticed some swapping of electrode. We also correct for some dipole inversion during the setup because of bad connection of electrode. We noticed that the lowest signal was 0.1 millivolt with a good signal to noise ratio. That was good for us. It means that we were in a relatively good condition. 97% of the data show standard deviation lower than 1%. So this dataset is really good. We kept 89% of the data, total of the data for the inversion. So we removed the outlier, the high standard deviation, and negative apparent resistivity. Unfortunately, we had to do this to use BERT that is not accounting for negative apparent resistivity. So we realized different inversions thanks to different software, BERT and ERTLab. On the two software, on the two models resulting, the anomalies, location, and amplitude are very similar. So this is a good indication on the robustness of the dataset. Different inversion have been realized in ERTLab also at different steps of the data quality processing. I mean, before correcting for the GPS coordinate error, after, before correcting for the dipole inversion, and after, and we see that each time the main anomaly location doesn't change, only the amplitude of resistivity is changing. So this gives a good idea of the good robustness of the inversion model on such high density and full 3D dataset. So we finally kept the model with the 2.35% of absolute deviation obtained after 13 iterations. Before starting any interpretation, we compare our 3D model to the 2D model previously measured. So for each of the 2D profile measured in 2019, we extracted this profile in our 3D model. We did not expect to get the same resolution as the 2D profile we acquired with 5 meter spacing, and we are more at 25 meter spacing. But we would like to see if we were able to recover the same global anomaly like on this profile, this conductive anomaly on the right part of the profile, and these two resistive anomaly. For all the 2D profile, there was a good, relatively good agreement with the 3D model. So this confirmed that our results are in agreement with previous work. Then we had to start with the interpretation, and we found that the resistivity was very, very heterogeneous over the landslide. So we have a look with the borehole geology analysis, and we found that there is no link between a borehole's analysis and resistivity. Actually, most of the borehole show shale pebbles in the sandy clay and gravel matrix with more or less sand, clay, and gravel. But this more or less unique geology is associated to very low to very high resistivity, so it's difficult to interpret resistivity with the geology. So to start the interpretation, we plot a threshold of resistivity. So in blue on this map, you have the resistivity lower than 100 meter, and in red higher than 400 meter. We also locate all the damaged building in dark red here, and we see no specific anomaly, resistive or conductive link with the position of damaged building. We noticed a large-scale anomaly here in the western part of the slope, which is actually aligned with the regional fault orientation, and we first interpret this as a low permeable fault along the schistosity plane. that could prevent the water from flowing down in this part, explaining the high resistivity. We can notice that just above this resistive anomaly there is a more conductive one, a shallow one, that is with depths lower than 30 meters. So we could interpret this as being the reservoir providing water to the entire slope. We can notice also that this resistive anomaly is actually separating certainly two different hydrological compartments. This is all the only thing we can say at the moment. So as you understand, we had no so much information for the interpretation right now. So to better constrain this interpretation, we are actively working on the construction of a 3D P-wave velocity model, where you can see here the first results. We will also realize a 3D S-wave velocity model from passive seismic measurements. We will use hydrochemistry data analysis and also 3D landslide displacement analysis for a better interpretation. Thank you for your attention.